Howdy, y'all, and welcome back to the channel. Let's see here. Excuse me. Today's lecture is brought to you by NOVAC, the Northern Virginia Astronomy Club. This lecture is going to continue my series on the solar system, and more specifically, it's going to continue the discussion I had in the last lecture, which is about light. Now we're going to talk about the thing that astronomers have a love-hate relationship with, and that is the atmosphere. Obviously, we love the atmosphere because without it, we would be dead. But when it comes to astronomical observations, it's really kind of a pain. It is exceedingly limiting. And so I'll go over the various ways how it is limiting and the ways that astronomers cope with that or deal with that. And in some ways, in some cases, that adaptation is very extreme. So yeah, and then afterward, after I'm done with that, I'm going to segue into a discussion on imposter syndrome and mental health in academia. I know that's kind of a juxtaposition, but I wanted to do that second video on that second part anyway. And so just thinking about my scheduling and all that, and considering this lectures are initially focused for GMU students, although of course everyone is encouraged to view them, but it is primarily intended for GMU students. I figure that, odds are maybe they'll stick around for my discussion of that, which I think is a very important topic for students to talk about, to hear about, particularly those students who are pursuing a life of academia, that they plan on getting an advanced degree and just staying in the academic environment. Although I guess it is kind of also applicable in industry. But anyway, I am now verging on babbling. So let us keep going. There we go. So many of you might be wondering why when you look at canonical images of telescopes, they're always high up. They're always on a mountain, or they're always on a mountain range somewhere, overlooking a vast place. Obvious examples of that are the Griffith Observatory in Los Angeles, the Mount Wilson in the not San Andreas. Man, I have forgotten basically the mountain range, whatever that is, outside of Pasadena. And then, of course, there's Mauna Kea, which is where majority of the American, most of them are actually international, but obviously it's in Hawaii, so it's an American observing site. And then you've got Chile and blah, 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 blah. Georg, howdy. So why is that? Why is it that we have we place these observatories in those locations specifically? And I do want to preface this by stating, when I'm talking about telescopes or observatories in this way, what I'm really talking about is optical telescopes and infrared telescopes. When it comes to radio, that's actually a bit different, and I will go into that after this. So when we look for an observatory, a place to place an observatory, when we're looking for a location to put a telescope, the primary thing that we're looking for is the minimal seeing, or what we call seeing, of the sky. And simply put, the seeing is the ability to see through the atmosphere as undisturbed as possible. One might ask why the char array, which I alluded to in the last talk, which is a optical interferometer, optical IR interferometer. It is a modern instrument, modern facility, still doing revolutionary work. Why is it that we placed that facility on a mountaintop right next to Los Angeles? Obviously, that seems to be a bit counterintuitive. And even on this slide, the third point is you want a dark sky. You want something that's far from city lights. Well, the reason for that is that the process of interferometry is light limited anyway. There's so many optics involved that you are brightness limited. You really can't see very faint with these telescopes as opposed to a single larger telescope. So that didn't really hurt us very much. But the primary reason is that Mount Wilson is actually one of the calmest sites in the continental United States. And what I mean by calm is that the wind, if there is any, is very linear, or what we call, it has a very laminar flow. And so the wind is not very variable in a way. When the atmosphere is variable, the atmosphere is comprised of many different things, nitrogen, oxygen, water vapor, so forth and so on, but it's also composed of dust, ash, in some cases, hydrocarbons, smog, basically, a lot of different things. And each of those particles plays a role in reflecting light or changing the path of light. And as the air moves, the constituents of that air, of those air cells, changes over time. And so what I mean by change is the density of the material can change, the composition of the material can change slightly. And so all of that affects the light which is transmitting through the Earth's atmosphere from the sky. So you want those transitions, or that sort of those cells, to be as calm as possible or as steady as possible. And so in most locations, what you have is a turbulent flow. And turbulent flow means that everything is very chaotic. It's just moving all over the place. The wind speeds are very high. All of that attributes to a very chaotic light beam as it's coming down. As I'll talk about in a second, light, when it's coming through the atmosphere, is kind of a game of Plinko, in that the light will bounce around greatly before it gets to the ground. So what we would, generally speaking, in order to get the best sight for the best seeing, the best view of the night sky without the atmospheric distortion, is that you want it to be calm, i.e. not very windy. So you want the atmosphere to essentially just stay where it is and not really change. You want to be high up because that limits, or that cuts out quite a bit of the atmosphere to look through. One of the reasons why we choose such high mountaintops like Mauna Kea or Cerro Tololo is that they are so high, they are basically at the limit of the troposphere. And so almost all of the weather is in the troposphere. And so the mountaintop is essentially over 90 plus % of the atmosphere. So you're always looking down on cloud layers. You never really have clouds above you. And the amount of water vapor that you look through is also minimized. And we find that water vapor is sort of one of the major what's the word I'm looking for? Bad guys, I guess. Bad things. Again, huge vocabulary. Bad things when it comes to affecting our observations. So that's really why we want calm, high. We obviously like dark so that we can see without light pollution, which is very much becoming a problem. And I will probably do a stream simply on light pollution. You want to be so you can see as faint in the sky as your telescope will allow. And then finally, you want it to be dry. Again, dry gets rid of the water vapor, and you also have fewer cloudy nights, so you can see obviously you can't optically and infraredly you can't look through clouds. So yes, and again, You also, incidentally, want it to be cold. Colder observation. I don't know if anyone has really experienced this, but if you're out in the cold, you may notice that when you look up in the night sky, the sky appears to be crisper. The stars seem to be more point-like than usual. And the reason for that is because, again, what's happening is in lower temperature environments, the water vapor is less. The humidity tends to be less in those cases. Light pollution, like I just said, probably we'll do a whole stream on this at some point. Light pollution is a problem across the board. It is, oh, Peter, I have many thoughts on satellites, and I've already done a lecture for our public series, Evening Under the Stars, about this. I hate them. I don't like them. Sam, I am. Real quick, specifically talking about Starlink. And I don't like Starlink, not because of Elon Musk, whom I are verging on despising. But the problem with Starlink is that the fact that it probably isn't needed. If you look at a couple of early studies have been done, and when you look at the cost effectiveness of satellite internet versus more basically ground-based fiber optic cabling, and simply the availability of internet access on the ground, Starlink isn't necessary. The only country where it is essentially actually cost effective and necessary for satellite communication is China. That's it. Nowhere around the globe is satellite communication necessary in the sense that it could be replaced with fiber optic cabling. Obviously, in a situation like the Ukraine, they've got way bigger problems to deal with at this point. But obviously in a peaceful environment, Starlink could easily be replaced. I will say one thing about Starlink before I move on. And there are other problems, like the fact that we're going to have thousands of satellites burning up in our atmosphere once all this is done at a very regular intervals. Anyway, like that. One thing I will say about Starlink is that they actually will talk to astronomers. They have actually implemented two things to try to mitigate the light pollution from their satellites. They've tried to make them darker by painting them black. They've tried to put on shields to essentially limit or literally shield the light from reflecting off the brighter parts. But unfortunately, in both of those cases, those solutions affected their bottom line. They interfere, or they degraded the efficiency or the power of the satellite. Effectively, it made them less efficient. It made them less effective. But they are talking to us, which is pretty unique in this situation. In terms of satellite telescopes, I will talk about that in more depth. Satellite telescopes, in certain cases, are actually necessary. So in that sense, I like those. I'm not against satellites at all, like all satellites. I'm against what are known as mega constellations, where you're putting up tens of thousands of satellites. So GPS, not a problem. I don't got any problem with that. But like I said, that's a whole different topic that I could go off for an entire hour about or more. Light pollution, like I said, and terrestrial light pollution is becoming a serious issue. We're trying to fight it here on the local level. We're getting a lot of pushback apparently from it. Basically, there are, again, a variety of different reasons, including health reasons, for why light pollution needs to be mitigated. Where was I going with that? So for the United States, and I think I quoted this last time, it said that in the United States, about 80% of people cannot see the Milky Way from their location. That pretty much means that indicates that a lot of people are urban. But you lose a lot, I think, both sort of in a way, philosophically and from an inspirational standpoint, particularly with children, if they can't look up and see the majesty of the night sky. So not only does it affect our work, but also I think affects just kind of humanity in general. So what is it about the atmosphere that really sucks? Well, from an optical IR standpoint, what it comes down to twinkling or turbulence. So as I like to point out, if you look up in the sky, if it twinkles, it's a star. If it doesn't, it's a planet. If it blinks, it's a plane. What is going on with twinkling stars? The reason why stars twinkle is because of our atmosphere. As I said, the atmosphere is composed of many different constituents, from gas molecules to dust particles and so forth. When a light beam or photon comes through into the atmosphere, it has a chance of, if it isn't absorbed by something, it has a chance to be scattered. Basically, it gets redirected by a molecule or dust particle or what have you. It basically gets redirected in one direction. It very quickly runs into something else, which redirects it into another direction. It basically plinkos its way down. And that plinko path is not the same for every photon. In fact, I would go on a limb and say that they are, in fact, unique for every photon. So instead of a photon coming straight down and hitting your detector and just staying there, you have a photon that plinkos down, hits your detector in a certain region, a little area, and then the next one comes down, plinkos down, it goes to somewhere else. And what that does is it causes the star to broaden in appearance. Basically, it blurs it out. So that angular resolution that you get from a telescope, what we call the diffraction limit, or the smallest details that you can distinguish as being distinct, that gets lost based on the atmosphere. So really, actually, if you have a telescope that is larger than 10 centimeters, from an angular resolution standpoint, unless you do something on the back end to mitigate it, you're really not gaining anything in angular resolution. This is mainly from a citizen science point of view. So if you're a citizen scientist and you have an 8-inch telescope and your neighbor has a 16-inch telescope, basically, from an angular resolution standpoint, your neighbor's not getting anything. The angular resolution is essentially going to be the same for the two of you. Obviously, they can see fainter in the sky than you can, but the atmosphere is going to basically blur out that advantage. It's really only when you start getting into very small telescopes where the diffraction limit of such a small aperture actually is larger than the atmospheric blurring effect. And you can see that from that evidenced from here, where you have a bright star that is imaged by a ground-based telescope that hasn't been corrected, and then you have an image that is that you have the same image of the same star field, the same star and field that you get from the Hubble. And obviously, in the top image, you have a bright point. Definitely know there's a star there. You have a couple of kind of fainter points hinting at other stars. But you certainly don't get the field of view or the number of stars that you do when you have a crisp, clear image. That the only thing that is affecting your angular resolution is, in fact, the size of your aperture. And this is time variable also. Well, yeah, this is time variable as well. So not only do you get a blurring, which is basically due to what we call scintillation, but that blurring also changes the size of the basically that central blob that you see. That also changes in size, time variable. So that's why we want calm skies and a minimal sky to look through. Is if you can minimize that effect, you can minimize the scintillation, the moving pattern, so the blob is smaller, and also you minimize the variability of how that blob changes, both of which affect the quality of your observations that you can make. This is an image that I took from from Mount Wilson, from the Chara Observatory. That is the Los Angeles Basin. What I wanted to do, my cell phone at the time, this was back in 09, 10, somewhere in there. And I have to say that my cell phone was not very sophisticated. It certainly wasn't sophisticated in terms of video, but I would have really loved to take a video of this, because what's fascinating to me about this is that Mount Wilson is about 5,500 feet up. So from a mountain standpoint, not real high, but 55 feet up is high enough that you are above what is known meteorologically as the inversion layer. That is the layer that traps a whole lot of that smog. And so when you're on the ground, if you can see stars, basically given that amount of light, you're going to see the stars twinkling like crazy. But if you're above that layer, say on the mountaintop, if you look up, the stars do twinkle, but they don't twinkle really much at all. As I said, it's a great sight in terms of seeing. But if you look down onto the city, those lights twinkle like crazy. It's actually quite cool to look at. I mean, they just bounce around, and in some cases they actually can change color. In extreme cases of atmospheric turbulence, you can actually take a white light and it'll oscillate between blue and red. So it also affects not just position but wavelength. But yeah, I really wish I had a video to show you that. It's actually a pretty cool effect. So this is Mauna Kea, which has a what's the word? Not mixed. Is a troubled history in a way. It is, like I said, an excellent site. All of those telescopes, you have the two white ones in the back are the two largest telescopes in the world. Those are the twin Keck telescopes. The squarish one, I believe, is Gemini North, which is an 8 meter. The silver one, the big silver one, that one, Subaru telescope, I think. I think I've got that backwards. I think the Subaru, which is mainly a Japanese lead, I think that's the square one, and Gemini North is the round one. I don't know. The little silver one, kind of in the middle, that is the IRTF, or the Infrared Telescope Facility. That is one of the few ground-based research quality ground-based infrared telescopes, and I'll explain why in a moment. The reason why this is a troubled history is that Mauna Kea is a sacred site for Native Hawaiians. And so when we requested that we build up there, we told the Native Hawaiians fairly recently that at some point they had basically said, 16 telescopes is enough. You can, please don't build anymore. If you build any more, you need to rip one out. And we're like, great. But as with many U.S. agreements with indigenous peoples, we kind of lied. And so we're trying to put the TMT 20-meter telescope on that site without removing anything else. And as you can imagine, the TMT is going to be a huge facility. And the Native Hawaiians got a little pissed off at us to the point that they blockaded the road to get up to the site. Jason Momoa actually went out there and was joining the protest for a while, so it got quite a lot of publicity. And so for the first time, I think ever, Mauna Kea actually had to shut down. There was at least one, maybe 2 nights where there was no data taken. Like none of the telescopes took data because of the protesting. Now, I'm not really going to get into who is right, who's wrong. I kind of side with the Native Hawaiians because there is a site in the Canary Islands which does not have this issue. It's a lesser site somewhat, but still, like I said, but I won't really get into it. Let's see. Well, this is a wordy slide. So this is basically talking about how do we overcome these limitations. I've already kind of talked about the second one, which is build it high up. The higher up you go, the less atmosphere you're looking through, and so the effects of scintillation and turbulence and seeing are mitigated. They're not eliminated, but they are mitigated. You can obviously put them in space, like the Hubble telescope, like the James Webb telescope. Then you don't have to worry about the atmosphere at all. Or you can do one major, that effectively all major research instruments facilities do, or observatories do. And that is that their primary mirrors are segmented, very much like the JWST. And the reason why JWST does it is pretty much the exact same thing, which I'll get into, which is called adaptive optics. So the idea here is, if we look at, so before I was talking about photons coming down and plinkoing their way down, you could also look at this from a wave phenomenon. Light comes in, hits the atmosphere, and is treated. I'm using this, I will explain in a second. We're treated as plane parallel. In absolute reality, is the light coming and striking the Earth plane parallel? No. But it is so close to being plane parallel that you would not be able to detect, really, with our instruments, any kind of curvature. So we treat it as a plane parallel wave coming through the atmosphere. And when it does so, the certain points of the wave are going to get distorted based on the material that it comes in contact with. So if you have smog here but not here, this is going to stay flat. This is going to get bendy. And so by the time it hits the telescope, that whole wave, which initially was basically straight, and in here you can think of it as the trough or the peak of the wave, gets all bendy, technical term, and it hits the telescope, and that basically results in these blurry images that we get. The way that we can change this or mitigate this is by making the mirror bendy. So we literally take the light coming down onto the telescope, we shunt part of it off. That then goes onto a camera. The camera then analyzes how bendy the light is. Again, very technical term. And then very quickly tells the adaptive optics system, which is basically pistons behind the mirrors, to deform in such a way as to cancel that out. Basically unbends the light, turns it into back into a plane parallel wave. That then gets bounced off this deformed mirror up to a secondary mirror, and then off it goes to the telescope or to the detector. So in this way, we get improvements like this. The Palomar Observatory actually is a single mirror, but it can still be deformed with powerful enough pistons. Deformed enough such. This is a very minor effect. So we're not in trouble of fracturing the mirror in any way, because it is a huge glass mirror. We're not in danger of breaking it or cracking it. But we can move it. We can distort it slightly. And so here is the Cat's Eye Nebula. The left is what the Palomar Observatory, which is 5 meters in size. So imagine it's got a very nice angular resolution that it's capable of. And so, but you get that nice blurry image. The Palomar telescope is in a mountain range just north of San Diego. But if you include adaptive optics, if you turn the adaptive optic on, and I've actually seen this in real time, which is freaking awesome, the thing just unblurs and just becomes really crisp, like you see on the right-hand side. Now we can definitely see the white dwarf, which is in the center, and again we can see that the plasma that has been ejected off of that white dwarf now has a lot of definitive structures, which will tell us quite a bit about how that material was ejected, what the magnetic fields were like when it was ejected, what they are like now. We are able to determine things that we couldn't before, because the image was so blurred. We couldn't have any sort of precision with our data collection. So that's primarily how we do this. And in actual fact, Keck beats out most of the time, Keck images will beat out Hubble images in terms of this amount of seeing, in terms of how well it can see very faint objects. The reason why you don't see, like, obviously Hubble gets all the glory in terms of the beautiful images that it creates. The reason why Keck doesn't is that Keck's field of view is typically very much smaller, and it would take a whole lot of observations, which are not necessary to replicate those kind of beautiful pictures. But with adaptive optics, we can actually get to the point where our larger telescopes can beat out our smaller telescopes in terms of seeing. In terms of seeing. These space telescopes that aren't looking through atmosphere. How does adaptive optics work? Like I said, the adaptive optics system works in that the light is coming down. So essentially the telescope is looking at a certain patch of sky, which is referred to as the field of view. Ours, for example, if you happen to look at my live stream where I was showing you how I was imaging M13, the field of view, or the part of the sky that I could see, was 25 by 25 arc minutes in 25 by 25 arc minutes squared. That's roughly the size of the full moon. In most cases, like, again, this is one of the VLTI or VLTs, very large telescopes. This is one of the VLTs. And their field of views are much smaller. Typically, they're on these, I don't know this one off the top of my head, but I imagine it's around a few arc minutes in size. So its view of the night sky is very, very limited. And so when we get this light from the sky, like I said, we're looking at a set field of view. Obviously, the bigger the field of view, the more stars you can see. That light gets sent, part of that light gets shunted off and sent to that computer system, that detector and computer system that then determines how bendy the light is so that it can then tell the mirror cell how to bend in order to compensate for it. The way it does that is by looking at individual stars. The individual stars, as I said, because of the blurring effect, is going to get bigger. It's going to blur out, and it's also the size is going to change variably. So the amount of the blurred out, the size of that blur, it can then tell the mirror, hey, you need to bend to this shape to make that ball smaller, that blob smaller. And then the variable part of it, basically this is happening in real time, and so it's constantly updating. The problem is that you require stars that are not your science target to do this with. You need to shunt the light from anything else in your field of view other than your science target. And in some cases, when you're looking at the night sky, your field of view is so small, you really don't have anything bright to compare that with. So adaptive optics wouldn't work in that case. There's no other star to shunt the light off for. Well, we have solved this problem in a very Dr. Evil sort of way. We have literally strapped frickin' laser on the head of the telescope, which you can see here. This is a composite image, essentially an image that is reasonably of a short exposure of the telescope itself, and then a much larger image or much longer exposure image of the night sky and the laser, and they've been superimposed on each other to make it pretty. But you can see that orange laser. That orange laser will go up to about 20 kilometers or so, and then it will hit a what's the word I'm looking for? Wow, chat just blew up. The light will hit a much denser layer of sodium, and it will basically reflect most of that light back down to Earth, or backscatter it. you can kind of think of it as a bat signal. And so you can aim what we call a guide star. This is a guide star laser. You can put that guide star anywhere you want. You can, and obviously you want to put it so that it is in the same field of view as your science target. And so that guide star is then used, the light from that guide star is then used to feed into the AO or adaptive optics system to correct that primary mirror. So that's the essence of adaptive optics. There is another thing that you can do, particularly on smaller telescopes. Maybe we are contemplating doing it with the 32-inch, and that is active optics. Active optics or tip tilt will actually correct for the bending of light by actually tilting the secondary mirror. It's not as good as adaptive optics. It really only takes out the variability of your blob. So your blob is going to still be as big as it is based on atmospheric blurring or scintillation, but at least it's not going to change with time. But like I said, that requires moving the secondary mirror, which, it's kind of problematic, particularly if you don't build the telescope with that built in the first place. All right, so we have a number of people have popped up. Safira, Peter, I acknowledge you, but I did not say howdy. Chris, howdy to you. Happy birthday again. Cygnus, good to see you. Dr. Clive, welcome as always. Dr. Nimrod, and company. So, and for those of you who haven't chatted, howdy all to you as well. And no, Clive, I have not shown any alien pics yet. Or have I? Another way that adaptive optics is useful, not only is it useful in getting those little fine details in, say, nebulosity, but it's also vital in terms of studies of binary stars or stars that are orbiting around a common center or barycenter or center of mass or center of gravity. Because if the blurring is sufficiently large enough, then you would see that pair of objects, those pair of stars, as a single blob rather than two distinct objects. And so if you can turn the adaptive optics on, and this is really what I saw a blob, they turned the adaptive optics on, and boom, I saw two stars. It was friggin' awesome. Really, really cool. So you're able to basically get rid of that atmospheric blurring and see those two objects as distinct. There is something called the Rayleigh criterion. The Rayleigh criterion has to do with how small of an angular resolution do you need in order to see those two blobs, those two stars, as separate objects. If your angular resolution is larger than the Rayleigh criteria, that means that you will not be able to tell that those two objects are in fact distinct from one another. If you are, and that is called unresolved. If it's exactly equal to it or thereabouts, we call that partially resolved. You can tell that there are two objects, but they sort of blur together and make kind of a dumbbell shape. And pulling out information from one of the other is a little bit tricky because you're going to have contamination of one object onto the other. If your angular resolution is well below that, then you are fully resolved and you can see the two stars as individual, and you can take individual measurements without having to worry overly much about contamination from the other one. What the Rayleigh criterion does not tell you or does not affect is the detectability of something. As you can see in this image, this telescope is detecting the light from those two stars. It just, in the first case, it doesn't have the angular resolution to tell you that there are, in fact, two different objects there. On the right, my right, I guess, The angular resolution has dropped or improved because of the adaptive optics system, and now these two things are now resolved. So it goes from an unresolved object to a resolved object. But in both cases, you are still seeing the same light that was coming before. The object is detectable. So the object on the left is detectable but unresolvable. The object on the right is detectable and resolvable. So that's that's mainly all of that is applicable to optical telescopes and to a certain extent infrared telescopes. What about everything else? As I said, the electromagnetic spectrum is infinite. It's huge. It has many different layers, many different regions. It's got gamma rays, which unfortunately do not turn you into a giant green rage monster. They just kill you. You got X-rays, you got ultraviolet, you got obviously visible or optical, infrared, radio, and so forth. So what about those? For those, things get even more complicated, or in a way, not so complicated. So what you're seeing here, hey Judy, I'm about to go buy stuff with your money, so it's going to be awesome. Thank you very much. Stuff for the observatory lights, nothing too spectacular, but it is for safety. So yeah, so for gamma rays, X-rays, and ultraviolet, thankfully for everyone else, and really for me too, the atmosphere is completely opaque, or thereabouts. Ultraviolet, a little bit of ultraviolet does get through enough to actually sunburn us and potentially cause cancer if you don't protect yourself well enough. But everything else, gamma rays, X-rays, and like I said, the vast majority of ultraviolet, you can't see through the atmosphere. The light does not penetrate the atmosphere and come down, which is good. Like I said, gamma rays, it's going to kill you. You're going to get cancer. You're going to radiation poisoning real quick if gamma rays can get to us. So thankfully, the atmosphere blocks that out. What that means is that if you are a gamma ray astronomer or an X-ray astronomer, or really if you're looking at the more energetic realm of UV, you have to go to space. There is no mountaintop high enough, no valley wide enough. Anyway, there is no place high enough on Earth where you can do this sort of experiments. X-ray astronomers, before the advent of satellites, really were limited by high altitude balloons. For X-rays, the atmosphere is transparent enough, down enough, or the X-rays do penetrate low enough that they can be detected by high altitude instrument or high altitude balloons. And that's still done today. It's way cheaper than sending a telescope up there. So in a way, it's simpler. You don't have to deal with adaptive optics because you can't see through atmosphere. Infrared is a pain, and that is probably the most complicated, because as you can see, there's this like forest of transmission. The orange corresponds to the opacity, or how opaque the atmosphere is. So you can see with gamma rays, X-rays, and ultraviolet, it's 100% opaque. Visible light, it's like 90% transparent. Most of the light comes down to us. With infrared, based on wavelength, and this graph is basically short wavelengths on the left, long wavelengths on the right. You go through infrared, and some of the wavelengths you can't see anything. Other wavelengths you can see fine. Well, kind of fine. So forth. The three popular near-infrared wavelengths we refer to as the J, H, and K bands. So in optical astronomy, we talk about the U band, or ultraviolet, very, very near ultraviolet, the blue band, the visible or green band, the red band, and then the infrared band. But when you're actually solidly into the infrared, you start getting into the J band, the H band, the K band, and then the L band, and blah, 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 blah. JWST primarily works in the infrared. It works with the JW on the more typical J, H, and K lines, and also, or bands, and then also in what we call the far infrared. But my point is, that you only can look through essentially very narrow parts of the very narrow wavelengths that are kind of transparent to infrared light, which is why the RTF is pretty much, I think I said it was the only, that's probably not true. It's certainly, there are certainly not a lot of them. It's certainly not as many as there are optical telescopes. That is why it's on Mauna Kea, because as high up you go, again, the primary reason why the infrared region is opaque is water vapor. The reason why it's so chaotic is because of the different vibrational states that water can reside in. Molecules, if you didn't know, vibrate. They basically, you can think of it as two balls on a spring that just constantly do this kind of number. And when I was talking about how atoms absorb light based on frequency, based on light on wavelength, the same is true of molecules. So instead of exciting an atom and sending the electron to a higher orbit, here you are hitting the atom and you're causing that vibration to increase or decrease. So it can absorb light, hence why there's opacity. There's a region of the IR spectrum you can't see at all on the ground, which is, again, one of the motivations for why we sent JWST up there. And Spitzer, for example, which is the kind of the precursor to JWST. Now we get into radio. And this is why I call radio observers dirty, dirty cheaters. And I ranted on this before. I'm going to rant on it again. The atmosphere is completely opaque or completely transparent to radio waves. So essentially, you get no atmospheric disturbance from in radio. So you don't have to worry about things like adaptive optics in radio because you don't need it. Also, and because of that, you don't need to put them on high mountaintops. In actual fact, you kind of want to put them on the ground, like the lower sea level. So when you look at places like the VLA, which is the very large array, it's in the middle of the New Mexico desert in Socorro. You want it to be a large flat area because, again, wind does play a certain factor. And so you want the little atmosphere that they have to work with, you want that to be as stable as possible, or as calm as possible. But yeah, it's completely transparent. And like I said, you can see during the day, you can see through light cloud cover. Cheaters. And then longer wavelengths we don't even bother with because, again, we can't see through that. Do you look at stars in the Aether band? No, we left that off years ago. So this, unfortunately, no longer exists. This is the radio telescope in Arecibo. It had the distinction of being the largest single dish radio telescope in the world. It is crud. How big is it? It's larger than 100 meters. I can tell you that much. What we did was we found a dormant volcano in Puerto Rico, and we literally put a dish in it. So that's a volcanic caldera that we built a dish into it. It's very old. It was built, I believe, in the 70s. And eventually, just because of funding issues and various other things, it kind of became dormant and neglected. And I think last year or the year before, one of those support struts broke and the thing just collapsed. It was scheduled to be decommissioned anyway, but we obviously didn't want the telescope, such a historic telescope, to be decommissioned in such an ignominious way. I was just about to get there. You may recognize this as the spot where Sean Bean died, or one of the spots that Sean Bean died. This was Sean Bean's lair this was used as Sean Bean's lair in GoldenEye. So if you haven't seen GoldenEye, at the end you will find something very familiar. They use a whole lot of CGI to make it look like it was flooded, and then they, in very Bond-like way, they unflooded it and There you go. So yeah, it's unmovable. It's immobile. The dish itself is immobile. So the only way that you can look at other places in the sky is that central gimbal, which is where the detector is essentially. And you can, by moving the detector around, you can basically change your field of view. And that is how the how Arecibo works. I don't know if I have. All right, that's interferometry, but I wish I had. I don't. Anyway, maybe I'll show it to you somewhere else. The largest telescopes in the world, the largest single dish radio telescopes in the world, there are two of them. One of which I know is active. The other one that I'm not certain of is in Bonn, Germany. I never seem to hear anything from that telescope. And the other one is the GBT, which incidentally does not stand for Great Big Telescope. It stands for the Green Bank Telescope. It is a 100-meter dish located in the mountains of West Virginia, right by a town called Green Bank. Why there's a town there, I don't know, because it is designated as a radio-free zone. One of the problems radio astronomy has to deal with its own kind of light pollution, in that radio transmissions will affect these things and can affect them quite surprisingly. So there are a couple of different radio quiet zones, the largest of which is a degree in latitude and a degree of longitude. Certain types of radio stations or radio emitters cannot be allowed in that. But in the smaller region, which is a couple miles or a couple of kilometers in size, it's kind of weirdly shaped, you can't have any radio signals. No Wi-Fi, no radio. A joker somewhere. Oh, if you go to this telescope, or go to the Green Bank, which I've done a few times, if you go to the lounge, essentially, where there's a pool table, pinball machines, that sort of thing, somebody put a AM/FM radio in there, just an AM/FM radio, not a turntable, not a CD player, not a tape deck, just the radio. So you can turn it on and you can spin the dial and you can hear a whole lot of static. And microwaves. Microwaves are, no petrol cars. You basically have to, in order to get to the telescope, you have to bike or you have to drive diesel. In terms of microwaves, I don't know. I was told that they really aren't allowed. I guess you can keep them in Faraday cages, but the Green Bank telescope is so sensitive that it can detect a microwave going off. A single microwave oven used by somebody in Green Bank contaminates that running will contaminate their observations. If you get close enough, cell phone signals are definitely detectable. So very cool. But the other thing I like to do, and I really wish I had a picture of it, and I will show it at some point. You have a 100-meter dish that is essentially the size of a football field, American football field, and it's steerable. I mean, this thing is ginormous. It just goes everywhere. Okay. The radio telescope is still active in Bonn. All right, excellent. Eifelsberg. I didn't realize that was what it was called. So yeah, apparently I am very ignorant of that. So yes, but it was in the movie Contact. This Arecibo was in Contact. It was in Goldeneye. I can't think of any other movies I saw it in, but yeah. Oh, you saw a documentary about it? Oh, they have to have permission. All right. So yeah. So, as I've said before, I highlighted interferometry, particularly in the optical and infrared part of the spectrum. In the radio or microwave, in radio is where interferometry was pioneered, because, like I said, you don't need to combine the light in real time. You basically you just look at the same object using the same dishes, or different dishes, and you combine the light on a computer after the fact. Or essentially combine the signal that you receive after the fact digitally. Or using analog tapes, way back in the day. But now interferometry has grown so ubiquitous that single dish telescopes are really not used very much in radio, or at least not that I'm aware of. The green bank does get used fairly often, but that's really only because it's so huge, and like I said, it's single dish radio telescopes are rare. With interferometry, like I said, you use multiple telescopes that span a different ranges and distance to simulate a much larger telescope. This is, and I probably should update this one. This is a schematic or CGI picture of the ALMA array in its early stages. ALMA is now complete, and I've already shown you an image of that. That was the YSO, or the young stellar disk, that shows clear evidence of planetary formation. That image was created by the ALMA telescope. There's also another one in South Africa called the SCA, the Square Kilometer Array. Kind of like that because I like SCA. So interferometry is the thing. We got Hubble. I don't know. I really need to correct this. That's not Hubble. That's the JWST. Like I said, Hubble is infamous, or not infamous, is famous for the observations it has taken. It has taken over 1 million observations. There have been over 100,000 publications using Hubble data over its 20-year lifespan. It is truly a revolutionary instrument, or was. And now JWST is going to push that revolution even further. A super huge interferometric telescope. I want that built. If I ever hit like the mega lottery, I might build one. I might build it. I might build the super huge interferometric telescope because it will be the shit. Anyway, infrared telescopes, as I said, for the most part, you want to put those in space. You can do ground-based infrared IR observing, but really you want them in space. Because another thing that you want the instrument to be exceedingly cold. As I'm also fond of saying, cameras are dumb. Cameras, which I'll talk about in the next lecture, cameras cannot tell the difference between a photon which is emitted from a star and a photon which is emitted from the wall of your camera. Anything that has heat or anything that has temperature is going to emit photons of one variety or another. And infrared is right where heat is located. You know, if you have IR glasses, you are basically seeing the heat radiated off of human or, organic bodies. So Spitzer was one of the 4 great observatory NASA. So NASA had the Great Observatories program. Hubble was in basically the UV optical, a little bit in the IR. Spitzer was IR. Then you had Compton, which was the X-ray telescope, and then you had XX Newton, which was the XXM, or the Newton telescope, which was the X-ray band, and then you had the Compton, which was gamma ray. All of those, from my understanding, I think Compton and XXM are still operational. Hubble is nearing the end of its life. Spitzer has already been decommissioned. Basically, it lost all of its coolant. And a couple of its, and at least one, if not 2 of its, basically wheels that it uses to spin around have gone kaput. And it's in an Earth trailing orbit, so we couldn't service it if we wanted to. There you go. Chandra. Oh wow, I got those completely wrong. Chandra is the X-ray telescope as part of the NASA Great Observatories program and the Fermi Gamma Ray Space Telescope. And as I said, I believe Chandra and Fermi are still active. All right, and that is where I will end this lecture. The next lecture, which probably will not be on Friday because we are doing a beer launch on Friday and Saturday. So the telescope or the observatory will be hosting the Aslan Brewery in debuting their Clear Nights beer, and so there's gonna be a lot of work being done during the day. So I won't be lecturing there. If I have time on Thursday, I will do my next lecture, but Thursday is looking a little tight as well. Anyway, the next lecture is going to be on detectors. I'm going to talk about the old photographic plates. I'm going to talk about photoelectric tubes. I'm going to talk about the modern CCDs that we use now, modern spectrographs. I'm going to talk all about that, and basically the actual instruments that we use to collect the light and get us the data that we need to tell everyone about it. So the Jehovah Witness Space Telescope, the Jawat. Oh, JW. Wow. It's all right. Yeah, it took me a little bit. Yes, that is awesome. I might actually start using that and irritating certain colleagues of mine. All right. Took me a while to figure that out. Longer than it should have. Okay, so that is the end of the lecture. And if you were here at the very, very beginning, I said that once that lecture was done, I would then give a talk about imposter syndrome and mental health in academia. I will probably, I will do my talk after I babble for a little bit. I will give that talk, and I will probably cut this. Well, I will cut this and post it separately. So if you're not interested in that sort of thing, thank you for being here. Thank you for watching this lecture. I hope that you found it enjoyable and informative, educational. As always, if you like this content, the content that I supply, including the mental health stuff that I somewhat frequently do, occasionally do, please like, share, and subscribe. And if you, of course, and my normal plug, if you would like to help us financially here at George Mason University in terms of our outreach program, please consider becoming a patron of mine, details of which are in the details of which are in my About Me section. I'm actually later today going to be using some of that well-earned Patreon money sent by Judy to go buy some red lights so that people don't, trip and die when it gets dark up there during public nights. So, not exciting stuff, Judy, but it is definitely vital, and I definitely thank you for your support in this. So I think we have a Gary. The astronomical clock of Prague is proof of the flat Earth. Okay, I will check that out. But anyway, so this entire live in my class still hasn't started yet. Happens when your lecturer is a clinician. Just real quick, I'm going to get into my spiel, but what class are you taking? All right, so I'm going to start off by talking about my favorite subject, me, just to give you a hopefully short synopsis of my educational journey, and I'm going to be basically pointing out certain challenges that I experienced along the way, and sort of just highlighting this. Just to be upfront, if you are not familiar with my channel or you're not familiar with my earlier videos or any of my videos on mental health, I suffer from basically lifelong mental health. It really became an issue when I was 13 in ninth grade, which I'll get into. I suffer from bipolar, borderline personality disorder, and generalized anxiety. When it comes to the topic of imposter syndrome, which very briefly is the belief that you are inferior to everyone around you, and you are basically fooling everyone, that you are not capable of doing what you are not doing the science, not doing the math, do whatever. You're not capable of doing what it is that you're there to do. And no one else has figured that out yet. And you are just waiting for that shoe to drop and basically be exposed as an imposter and kicked out. Seizures and epilepsy. Ooh, cortical secrets. Now that sounds cool. PhD, Dr. Safira. Nice. Or as I would say, proto-Dr. Safira. So that's basically me. I suffer from it, imposter syndrome. I still suffer from it. I often feel like I'm the stupidest person in the room, particularly when I'm around colleagues. In terms of the 4 doctors of flat Earth, Clive, Phil, and Tony, I feel like I'm the stupid or dumbest one of the 4. So it is something that I deal with. Is that true? Am I the stupidest person in the room? Am I stupider than those other 3 gentlemen? I don't know. And really, it's not that important, as I'll talk about later on. So, in 8th grade, I somewhat distinguished myself by being the number, based on standardized testing, I was the number 1 student in my county for history, English, and science. And so my those accomplishments, based on my and also based on my academic record, I got admitted to the International Baccalaureate program, which is, the cream of the crop of students and teachers and all that, yada yada yada. I don't have a very high opinion of the program, but anyway. So I got accepted into that, and I went in, and obviously this is the best of the best, and because of various reasons, I felt a lot of pressure, and my mental health, I want to say broke. Not really the right term, but I went in crisis. I went in the hospital, and long story short, I graduated my 9th grade year with a 1.7 GPA. I then went back to my, after 9th grade, I elected to go back to normal high school, and I graduated 72nd in my class with a weighted 4.1 GPA. I dug myself out from a 1.7 to a 4.1. It is an accomplishment that I still feel a matter of pride about today, that I was able to do that. Now, the thing is, particularly early on, and to a certain extent now, when I look at that period of my life, what immediately comes to mind is I failed. I was put into a situation where excellence was expected, and I failed. I was not up to the challenge of being with the intellectual elite, as it were. The reality of it, the objective reality of it, and then when I think of that, I then take that to another level and basically say that I'm a fraud. That this is yet another piece of evidence that says, I ain't worth shit. That I don't belong here or anywhere else. That I don't deserve the things that I've gotten, particularly in the academic field. In the times that I can objectively look back at that period of my life, what I fail to realize is I earned that. I got into the International Baccalaureate program. I got into the IB program. I was, I guess, smart enough or academically able enough to get into the program itself. So that is a huge accomplishment. And then at the time, particularly what I failed to realize is that bipolar, any mental illness, is an illness. And really, it's a physical illness. The chemicals in your brain, the neurochemicals in your brain, physical neurochemicals in your brain, are not functioning in the same way as a neurotypical person does. You feel debilitating effects to that because of that illness. You have obstacles that you need to overcome that others may not. And what I didn't realize was, like anyone with another disability, like cerebral palsy or what have you, something that is physically limiting. What I didn't realize was I needed to cope. I needed to do things that others didn't have to do in order to keep myself healthy. It is nothing to be ashamed of in any way whatsoever. It is just a fact of life. Good, bad, ugly, it is simply a fact of life. Like people train to keep themselves physically healthy. They eat, your diet, your exercise, whatever it is you do to keep yourself physically healthy. You also have to do things to keep yourself mentally healthy. And I didn't do that. I didn't have the training for it. I didn't even know that this was a thing. I didn't, my culture, my upbringing, mental health really didn't exist. Mental health, like batshit crazy, that existed. People who are insane, those people existed. The nuts in the hospital, those existed. Anyone like me who had emotional dysfunction, I just had poor character. I was just broken. I needed to suck it up and figure out how to be a better person. It was only until later that I really, probably far too much later. I won't say should, but it was much later before I really internalized and accepted that idea that what I have is an illness, and it's something that I can cope with, and it is something that I have to deal with. Do I deal with it very well? Do I sometimes get knocked down, fall over or what have you? Yeah, I do. As my YouTube channel attests, there was a extremely last couple weeks or so where I was just in a really bad place and just streamed to get it out. So yeah, I'm not perfect. No one's perfect. I had a relapse of sorts and I dealt with it. And now I'm here doing this. So, on with the story. So during that time, what I failed to recognize, and this is a common thing, I believe, I've been told this is common for folks in my position, particularly those with imposter syndrome, is that we often fixate on the negatives. We often do not objectively analyze or judge a situation. When I look back, like I said, when I was younger, when I look back on the situation, I was like, I failed out of the IB, and I only graduated 72nd in my class. So I didn't look at it in terms of I got into the IB program and I pulled my ass up from a 1.7 to a 3.1 or 4.1. I didn't acknowledge those facts. I did not acknowledge those as being, good enough. The way I was raised is if success is mandatory, and you don't celebrate that which is mandatory. It's mandatory. You just do it. So really, the only thing that you really kind of a judgment on or what have you is failure, and that judgment is always negative. So I got it. Well, so I went to the University of Florida. I still did well enough that I got a full ride. I did not have to pay tuition or fees during my 4 years of undergraduate work. Well, I would say but actually my parents had to pay for books and room and board for at least the first 2 years, and then I got a job, and for the last 2 years I was pretty much self-sufficient. And I went in. I have always wanted to do astronomy ever since I was in the 7th grade. I wanted to do astronomy. Initially I wanted to do cosmology until I realized my brain is not built for that sort of thing. Way too much math, way too much complicated math. Anyway, but I knew I wanted to be an astronomer. I knew I wanted to be, and obviously that hadn't changed. That never changed. But I went in and I thought, I want to be this type of astronomer. I want to be the stereotypical astronomer, the one that the professor who teaches, does research, has grad students, all that. And I went in there and I wanted to double major physics and astronomy. And I did well my first year. I did very well my first year. And I thought, obviously I did very well. I can do more. And so I overloaded and I broke myself, I guess. I had to drop a couple classes. I actually got an E. University of Florida is actually a great place in that their grading system does not skip the letter E. It's A, B, C, D, and then E, not F. So I failed linear algebra because my professor was a prick with ears. And that set me back. That actually required me to choose between either astronomy degree or a physics degree, and I chose astronomy. I could have graduated. Going in, I had enough credits that I could have graduated in 3 years. And I didn't. Because of certain factors, because of my disease and other things, I actually had to withdraw for a semester. But I came back and I finished up my degree. Now, what I learned about my undergraduate work, my undergraduate degree or undergraduate experience, sort of if I had to do it all over again, is, again, I felt this imposter syndrome. Whenever I was in study groups with other physics majors, particularly, or other physics and astronomy majors, again, felt like the stupidest person there. I felt like I really wasn't able to contribute too much to the discussion or to solving the homework problems or what have you. And that was what it was. There was, at the time, I did not handle that very well. Excuse me. There we go. Paul Dirac was at the University of Florida. Really? Well, Dirac and I never crossed paths. But anyway, I didn't have the tools. Again, same with my high school career. I did not have the tools. I did not know how to exercise or take care of myself mentally. I really just had to push through it, which sucks and has a very low success rate from one situation to the next. But that's all I could do. That's all I had, was to basically just push through and just say to myself, I got to do this. Funny enough, fear is what motivated me, and fear is a great motivator in a way, because I, again, had this absolutism idea in my head. If I didn't become an astronomer, if I didn't graduate and become an astronomer, I was going to be homeless. There was no in between. There was no, working at a grocery store or finding a job as a data input or technology or what have you. There was no middle ground at all. I was either going to succeed, get my degree, or I was going to be homeless. And I didn't want to be homeless. So I managed to just push myself through it, which was probably even more damaging. After getting my BS in astronomy, I went immediately into grad school. At Florida because I had this idea that my life had to be a certain way. In order for me to be not an imposter, I had to go undergraduate to graduate, go from my BS to my PhD, as is typical for most people, just straight through. And again, if I could not do that, then I was a failure and I wasn't worth anything. And again, probably end up homeless. My master's career, I managed to get my master's degree. It was non-thesis. I did do a research project comparing dynamic mass to dark mass in the Whirlpool galaxy. but it didn't get published. It really wasn't a great thing. I basically eked out of my master's degree. I eked out of getting my master's degree in astronomy at the University of Florida. It was a miserable time. If I had to do it again, I would have definitely taken a gap year. I needed to recover from my undergraduate. And again, to stress it, I was ill. I was sick, and I was not taking care of myself. And then I put myself in an extremely trying or extremely intense environment. And as it turned out, also toxic environment, because the University of Florida's department at the time sucked ass. So all that can basically, I went in already ill, already essentially handicapped, and then I was not in a supportive environment. I was not good, and my imposter syndrome festered. It grew, and I had to take. I then had to go into basically try to find employment. Again, that mentality of, I have a master's degree in astronomy. I have to be in astronomy. If I'm not in astronomy, then I'm basically homeless. So it didn't even occur to me to really branch out and try to find jobs in, say, the computer sector, which I was marginally. I did know how to code at the time. Not well, but I could code. I didn't think to go into the computer sector or industry or what have you. Astronomy. It had to be astronomy, or I was worth nothing. And, I applied 20 different places. And the only place that actually called me back was Emory University, and they ultimately hired me. And I was a lab instructor there. I eventually got to a point where I basically took over the astronomy labs, redesigned them. I also helped basically set up the 24-inch telescope that they had there, and basically set up and train folks on how to use it. But eventually that just became unsatisfying. And also, again, I had it in the back of my head, you're not a PhD, you're not worth anything. So eventually I said, actually, I had to, I got fired from Emory University. And I know some people out there are probably going to snip that and use that against me. But, it is what it is. I got fired from Emory University for bullshit reasons. Not going to get into that. So I took my retirement, pulled it all out, and used that to survive for a year. And I went to the Georgia State, and I said, hey, I want to enter the PhD program. I had kind of dabbled back with it back in 2003, but I was like, hey, I want to I want to become a grad student. I want to get my PhD. And they were like, okay, if you pass the first qualifying exam, you're in. I got an 88 on it. So obviously I passed and I got in. It took me 8 years from that point to get my PhD. Typical for astronomy is 6 in the States. It's 6. Some people can do it in 4. But on average, it's 6. It took me 8. During that time, there were some personal issues that I had to deal with. My mother quickly developed dementia. I had to take care of her. I also, again, was not very adept at taking care of my own personal health. And I had to go into an inpatient facility for 3 months. So that obviously set me back. But I did it. I buckled down and I did it. Because during that experience, while I wasn't very good at it, I was learning coping tools. I got into therapy. I started learning coping mechanisms, and I used them. And they were enough to get me through. They were enough to get me to the point that I could graduate, that I could get my PhD. And yeah, it's true or not, objective or not, I consider it my greatest accomplishment to this day is getting a PhD. As I was told on during my graduation ceremony, I'm part of the 1%. I'm a 1%er in the sense that only 1% of the population has a PhD. I don't know if that's true or not, but that's what they told me. And so from there, did my postdoc for 2 years, and then went to the university, the Louisiana State University. Didn't like it. Came here, applied for a position here, and got it. And the rest is history. So, when it comes to mental health, let's first start off with that. If you suffer from mental health, now mental health is not monolithic. There are different types of mental illnesses, and even certain mental illnesses can come in chronic or reoccurrent or situational, like depression, like major depression disorder. It can be reoccurrent, or it can be that an event just triggers that chemical sort of it just flips a switch, as it were. I don't know. I'm not a neurochemist. It messes with those chemicals and sends you into a depressive episode that eventually you can work your way out of, and may never ever happen again because you had that one really traumatic incident. But it is an illness, and you need help with an illness. If you break your leg, you go to a doctor. If you get cerebral palsy, you go to a doctor. You don't try to stick it out. You don't try to come up with ways to fix it yourself. You don't pull yourself up by your damn bootstraps. You go to a doctor. So if you have mental illness, go to a doctor. Get medication. Definitely seek therapy. Medication is only going to get you so far. No matter what kind of bullshit the pharmaceutical companies or the psychiatrists tell you, it's only going to get you so far, depending on the level of your illness. But therapy is wonderful. Actually, I recommend therapy to everybody because it taught me coping skills, and I had to put them into practice. And that also was a struggle because, again, I felt like crap. I had an extremely low self-esteem, still do. And it's really hard to convince myself to help myself when I think that I'm already a piece of crap. When I'm in my better states, objectively speaking, I realize that, let's assume that I am a piece of crap. That's not going to change unless I improve myself. And so I have to use these coping mechanisms. As much as they suck, as much as they tire me out, as much as I don't like using them for the most part, I do. And I can put a reference, if I remember correctly, I'll put a couple of references to books in the description that detail these mechanisms that I use. Primarily, that's cognitive behavioral therapy. These are the coping skills that I use. And, you have to take care of yourself. You have to take care of yourself physically, and you have to take care of yourself emotionally. If you don't, then just like a fat guy on a couch guzzling beer is probably going to die early of a heart attack and isn't capable of doing certain jobs because they are just not physically fit enough to do them. If you're not mentally fit, there are certain jobs you won't be able to do. And that fed into my imposter syndrome because, there were times when I was not really capable of doing what I wanted to do. I mean, it took me 8 years to get my PhD. But when it comes to imposter syndrome, the thing that I try to keep in mind as much as I can is, being the smartest person in the room, that's great. That's awesome. I think that's probably more genetic than anything else. Or it's a sign of dedication and hard work. I don't need to be the smartest person in the room. And objectively, I could also live as the dumbest person in the room. What matters is my job. What matters are my goals. And that's another thing, is you learning to set expectations, reasonable goals, not pie in the sky. For a long time, I wanted to be the best scientist, or one of the best scientists. I always said I didn't want to win a Nobel Prize. I don't want to be the best scientist. I just want to be among the best scientists. When I started thinking about doing science communication, I was like, as natural for me, I was like, yeah, I don't want to be Bill Nye, but I want to be kind of Bill Nye adjacent. I realize that is probably never going to happen. It is a goal in a sense. That is what I aspire to. Bill Nye is a hero of mine, but that's not my goal. That's my dream. My goal is to educate. My goal is to provide lectures, is to lecture, is to teach on a more personal level with my interactions with the undergraduates. My goals are to be as intellectually honest, as intellectually curious as I possibly can. If I meet those goals, if I do what I can to meet those goals, then I've done enough. And I'm great. Then I don't like using judgmental, subjective words like good or whatever, but that's enough. That's sufficient. I am fulfilled by that. I look at that and I say, hey, I've done the best I can. I have done what I need to do. And, that's, if someone else out there is better than me, of course there's going to be someone out there better than me at this, because I'm human. And, I'm a fantasy nerd. So, in books, the famous thing is no matter how good a swordsman you are, there's always going to be a better one out there. That's a truism for all things. No matter how good I am at something, someone else is going to be better at it. And that's irrelevant because they're not here. They're not doing what I'm doing. And if I accomplish what I want to set out to do, it really doesn't matter if someone could have done it better. I've accomplished it. I have helped people. I have taught. I've imparted knowledge. I have hopefully inspired students and others to be honest, to be curious, and to treat people with respect and love. Those are the things that I want out there in the world. So it doesn't matter to me, or objectively speaking, I try not to have it matter to me where I am in terms of everyone else. And the thing is, and also sort of more to the point, is this is made for students. This is pretty much for students. Is you got into college, you did the work, you got the grades, you got into college. You deserve to be here. You deserve to be a student at George Mason University. If there are students out there at other facilities, you deserve to be a student at that educational facility or institution. You know how I know that? Because you are a student at that institution. The admissions boards, they're not idiots. They are looking for the best students they can possibly get because their reputation depends on it. If they get the best students and those students become even better and go out in the world and become awesome at whatever they're doing, one, they can people can brag about it. Two, they can hit you up for money and get money from you as an alumni. So they want you, they want the best people. So if you're here, you have accomplished that. You deserve to be here. If you're a grad student, same applies. You did the work. You managed to get, you did the work. You did the exams, all that kind of good stuff. You got accepted into a PhD program, which is amazing. PhD programs are highly competitive. They are not, that is even more an accomplishment in my eyes than getting into college itself, like undergraduate college. So you even more deserve to be here. You're not an imposter. You deserve to be here. And again, if there is a student out there, if one of your students is better than you, gets better grades, seems to pick up on concepts a lot better than you or what have you, great, fine. That's awesome for that person. But again, that's not your goal, really. Your goal, hopefully your goal isn't to be the best person there, to be the smartest person in the room. your goal is to get an education. Your goal is to learn new things, to research, to be able to satisfy your love or satisfy your curiosity, and ultimately to get a job and to do whatever it is that you're going to do with the money and the position that you're going to get. Hopefully you're not in this for being the smartest person in the room. So now how is it, that's all well and good. That's, me telling you that is it is what it is. You can accept it or not. I know if I've been told that over and over again throughout my life, that I am a good person, that I do deserve the things that I have, and but particularly for me, I have a hard time accepting that. My illness tells me otherwise. My illness doesn't like the idea of me thinking well of myself. Whatever reason, whatever physical reason for why, I just don't think that way. At least initially, I have to coach myself. I have to cope to accept that. So here's my unsolicited advice. If you're in academia and you want to stay in academia, because academia can be hard. Academia can be toxic. I'm assuming that's the same everywhere, but I can only speak from my own experience, and that is that academia can be difficult. It can be trying, both mentally and physically, and it can be toxic. Certain professors can be bigots. They can be, they can basically have the opinion you need to suck it up. If you can't handle this emotionally, you don't deserve to be here. Those people can fuck right off. In fact, they can continue to fuck right off. If you are a professor, if you believe that if a person is not emotionally capable, if you believe that breaking down, crying or having a severe emotional reaction, not being able to just immediately get up, bounce back or whatever, that needing that time to cope, that time to heal and to get back into it. If you do not accept that is a reality for folks, you can fuck right off. You can continue to fuck right off until you get to the wall at the end of fucks. Then, because I believe in you, you can climb that wall and continue to fuck off. People need to be nurtured, and you would not tell that to somebody who has no legs. You wouldn't tell them, well, you need to figure out you need to just get up and kind of crawl on your hands. And if you can't crawl on your hands, then you don't deserve to eat. I mean, no one, unless they are a complete psychopath, is going to tell that to someone. Is not going to say that to someone. So the same applies. If a person has a mental illness and they need that, then that shouldn't be in your. Anyway, for the students, it's going to be toxic. You're going to run into that, sadly. And so what my advice, again, unsolicited advice, is, as I've said before, if you suffer from any kind of mental illness, and really, even if you don't, seek out counseling. If the emotional part of it is becoming dysfunctional, if it is causing you to not be able to perform, to meet your goals, to satisfy your goals, then you need to do something about it. Seek out therapy. Seek out the tools that will allow you to emotionally cope with it, with whatever it is you're going through, whatever it is you're experiencing, which is completely valid. Any emotion that you feel is completely valid. What is important is how you deal with that feeling. That is what's important. That is what, I was going to say that's what you can be judged on, but really you shouldn't be judging anyone on anything. But that is what's important. That is what's going to help you get to your goal, to accomplish your goal. So you need that help. Now, obviously, therapy is just one piece. What I found to be very helpful, particularly as an undergraduate, and drugs are bad, drugs are bad, okay, but I found a group of people who were kind of just like me, or at least they were good students. They had ambition. They wanted to get into academia or become lawyers or professors and all that kind of good stuff. They had goals very similar to mine, and I hung out with them. They were good people. They are good people. I drank, did drugs with them. I relaxed, and I opened up. Obviously we didn't. I didn't just spill out whatever it is I was feeling to just everybody when I around the beer circle, around the bong. But I would just vent. I would just get it out there, and take a risk and admit statistical mechanics scares the fuck out of me. I don't think I can make it. I don't think that I can understand that. Chances are someone else feels the same way. And normally I don't go into the whole, I feel the same way you do, and rah. But really, it can open your eyes. It can be comforting to know that you are not the only person struggling here. So talk with people. Don't isolate. Do not isolate. Isolation is only going to lead to more dysfunction. It's just going to, all you're doing is locking yourself in your own thoughts. And if you got shitty thoughts, it's going to be a shitty experience. Kind of logical. So open yourself up. As much as it sucks, as much energy, as it's going to take energy, it may take energy. Find people, open up, relax. Take time to chill out. Like I said, I used alcohol and drugs. I was responsible. I handled them, whatever. Do it a rock climb. Do whatever it is that you like to do to keep yourself relaxed, keep yourself from fixating on this shit. Because this isn't all life is. This is not all life is. Branch out. Keep yourself healthy. In terms of another valuable thing for students is communication, particularly if you are communication with your professors and particularly communication with your advisors. Because if you are struggling and don't tell anybody, they're not mind readers. They are not going to know. Particularly with professors where where they're teaching a class that has hundreds of students. I know from experience, unless you tell me, I'm not going to notice. It's the reality of it. I cannot notice the minutia of individual students when I have 200 of them. It's just not possible for me. So unless you come to me, unless you go to your professor, they're not going to know. And again, there are assholes out there. There are toxic people out there. And if you go to them and you say, I have a problem, this is, I need an exemption. I need more time. Whatever it is that you need, and you express that to that person and they dismiss you or they reject you, that is going to happen too. But I'll get into how to do, or what my unsolicited advice to that in a second. But hopefully your experience is going to be is going to not be that. And your professor, because they know what you're going through, can work with you on seeing to your needs, accommodating you, making sure that you can accomplish your goals, which is to pass the class and to do, or do well in the class. Communicate with your professors. Let them know what you're at, or where you're at, and what you need. Because if you don't, you're not going to get their support. And in academia, particularly as a student, you need that support. And I'm working on my end to tell my colleagues that they need to basically be supportive. And so I'm doing my best to change certain cultures. But even if I succeed, even if everyone in my department becomes really, really chill, really, really cool, unless you tell them you need help, they can't help you. With your advisor, if this is for PhD students or master's students who are looking, or thesis-based students, if, again, communication is vital, because there is an expectation. There is definitely expectation that you need to be doing work like a job. You need to be putting in your 40 hours, or for some people, 50, 60 hours. And if they don't really see you doing that, they're going to just assume you're not doing that. And in my case, that was pretty good assumption. And so they're going to be like, why isn't Rob here? Why isn't Rob in his office? Why isn't Rob responding to my emails? I was in a place that was really, really crap, really, really shit. I've already sweared so much, so I was in a shitty place. But I didn't tell them that. I didn't tell them that. I didn't tell my advisor, who was really, really cool, or is really, really cool. I didn't tell my advisor I needed that help. And so they didn't know what to do. They just knew that I wasn't meeting my goals. I wasn't meeting their goals. And so when I finally did tell my advisor, Russell White, what I was going through, he was supportive. He gave me the extra time. He gave me the, I wouldn't say that he gave me advice or anything like that, because it was obvious he had never really dealt with someone like me before, or someone with my illnesses before. But he was cool with it. He wasn't judgmental. He gave me the support that I needed. As I said, not all professors are like Russell. You're gonna meet toxic ones. If you meet in a toxic environment, if you get into a toxic environment, if you have a professor who is really just a prick with ears, what I would, again, my unsolicited advice is to either just double down on those coping mechanisms. Double down on those coping mechanisms, and when you have questions, go to someone else. Go to the TA if there is one. Go to your classmates. Go to another professor. Do not go to that person, because that person is going to treat you like crap and is going to make your situation worse. Go to someone else. And I stress that. Go to someone else. Don't just, I can't go to my professor, so I'm not going to go anywhere. Go somewhere else to get help. There's no shame in it. It is vital. It is. We all have to. No one is perfect. No one is Superman or Lex Luthor and can accomplish everything by themselves. We all need help. And if you don't get help, you're just not using the resources that you got. And why not use resources that you have in order to get ahead? There's no shame in it. There's no judgment in it. So if you have a prick with ears professor, then do that. Blah, 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 blah. Where was I going with that? If you don't, great. They can help you. There was something else I wanted to say. If you don't want to deal with that person, so that in that case, that would be in a situation where you can't escape it. That professor is the only person teaching that class, or you just can't take any other class. If you have an alternative, take it. Get out of that class. Find out, also, before you do that, find out, is this professor a dickhead? Talk to other students. And ask, is this person a dickhead? And if they tell you no, go to their class. Become their student. And also, let your professor know, let your department chair know. If you're a major and your professor is, your professor is in the department of your major, let the department chair know that you're having difficulty with that person. I'm not trying to say get that person in trouble. I'm not saying go in there and try to get that dude fired or that woman fired or whoever. I'm just saying let the department chair know, because again, communication is vital. Unless the department chair is told that there is a problem, they can't fix it, or they can't work to fix it. They can't approach that professor and be like, listen, your approach to your students isn't working, is actually causing harm. And, they can work out how to mitigate that. So if you can leave and tell the department chair, and that really actually just tell the department chair anyway. So, take somebody else. Just get out of that environment as much as you can. Now, for grad students, if you're a grad student and you have a shit advisor, you have a toxic advisor, drop them. Just drop them. Go somewhere else. And I know, all right, well, this is the only person who does exoplanet science in my department. How am I going to, and I really want to do exoplanet science. What am I to do? How am I, if I go to this other advisor, I'm going to learn about AGN. I don't really care about AGN. And that's not the professional way that I want to go. Well, two things on that. One, if your advisor's toxic, the chances of you surviving through grad school and actually achieving the goal of getting a PhD and being in a situation that you can get to a large and actually explore the possibility of having a successful career in exoplanet science are less, probably significantly less. So you're putting yourself through a lot of trauma. You're potentially putting yourself through a lot of trauma for potential failure in a way, a potential failing your goals, not succeeding where you want to be. Second thing is, most astronomers, I don't know about physicists, but most astronomers do not actually stay in the field of their dissertation. My advisor is an exoplanet, or Russell White was an exoplanet scientist. Guess what he got his PhD in? AGN. I'm not saying that was the situation that he was in, but many professors many of my colleagues, they got their PhD in one field or one subfield of astronomy, and they moved on, and professionally they moved on to another one, because they, for reasons I can't speculate on them. I would think that maybe one of the times was they thought they wanted to do cosmology, realized that kind of sucks, and there's like, no, I want to do planetary science. They may not have initially thought, hey, I want to do planetary science, but then they investigated and they're like, woo, rocks are cool. Whatever. If you have a toxic advisor, leave. Do not try to. My advice: do not try to work it. Do not try to work it out. Try to go to your advisor and be like, yo, you're micromanaging, your bigotry is really causing my ass to clench. Please get off my ass. I need you to get off my ass. And if they won't, or they won't change, they won't work with you, leave. Go somewhere else. Get another advisor. You'd be surprised. It's still astronomy. I mean, and you can always return if you love exoscience or exoplanet science. You get your you get your PhD in AGN. Always go back. It's a little trickier, but you can do it. I've seen it done. So yeah. All right. I've been at this for an hour. Hopefully that was useful. Hopefully that was, hopefully you get something out of it. I didn't mean to go for an hour, but I'm a long-winded son of a bitch. So, all right. Let me just quickly, Judy, yes. Contact me anytime you want. That goes for everybody. My email is in the About Me. If you've My Discord is also in the About Me. Hopefully the invite hasn't expired. They say that it never expires, but they lie. Join my Discord. DM me. Find me on Discord. Whatever. Yeah, contact me if you want to. I have no problem with that. Which reminds me, I need to actually give Dr. Bob a call. All right, let me look through the chat here and see if there's anything. Let's see. I told myself my imposter syndrome didn't start until junior year in undergraduate. I told myself it's because I'm not pure physics major like my peers. Yeah. I have found, for me, I should say, that I had a hierarchy of cool, or I had a hierarchy of what's better or what's more important. So, yeah, for me, the astronomers who do active research, I think are, for a long time I thought are more successful, more important, more worthy than science communicators or educators at the PhD level. I just felt that way. And so, yeah, it seems like I get the feel, or I can understand if this is even remotely applicable to you. I understand the idea of, being a pure physics major is just more important or more impressive than, being a physics or, physics biology double major or whatever it happens to be that you are not a pure physics major. And so, yeah, I get that feeling of a hierarchy of coolness or a hierarchy of worth. Let's see, my obtainable goals. It's said that is a test of true friendship. If you need to dispose of a body, that's what separates your true friends from your fair weather friends. Is a true friend will help you hide a body. Very, very true. Very, very true. Thank you, Ali B. When I get to know you better, I'm sure I will like you too. I'm assuming you're talking about me. Biophysics. I figured it was in the bio range. Which meant my sacrifice additional math and physics for biochemo. Yeah, I got down on myself because I haven't taken a chemistry class since 10th grade in high school. Because astronomy majors, we don't deal with chemistry. I mean, some of them do. Yes, some of them do, actually. They actually do quite a lot of chemistry. But generally speaking, it's not required. Yeah, like I joke, there's hydrogen, there's helium, and then there are metals. We just really wash our hands of that. But I got on myself for that because I realized that, physics majors, they had to take chemistry. And they had to do a little bit more math than I did. And they also had to take, they were required to take classes that were optional for me. I never took a class on quantum mechanics. I elected not to. I elected to take an astronomy course instead. And, I still feel a little, I still get down on myself for doing that. So yeah, I think I get that too. Anywho, oh shit, it's 5 o'clock. I've got to go let some students up to the observatory so they can fiddle with, speaking of cameras, so they can fiddle with our new IR camera, which, as I was saying before, you really need to be high up and all that kind of good stuff. I have my doubts as to how effective this camera is going to be, but we're going to try anyway, because IR science is cool. Literally. Anyway, so yeah. I will see you the next time. That will be, like I said, that'll be a lecture on detectors. Hopefully tomorrow. If not tomorrow, then Sunday, because the whole beer launch thing is Friday and Saturday. There was also something else I wanted to put out there, and I completely forgot what it was. A separate video that I wanted to do. Oh, well, it'll come to me. So yeah, peace out. Be good to each other. And clear skies.